This video is over Lesson 74, Simplifying Square Roots, and it is for my pre-algebra classes. So ladies and gentlemen, today we're going to take a look at what's called the product property of square roots. And it says that the square root of AB, so this is our product here, okay? So the square root of a product, so something times something, will equal the square root of the first thing times the square root of the second thing, the square root of A times the square root of B. So essentially what we see here is we see the square root basically distributing over the multiplication so that each of the things that we're multiplying by can have their own separate radical. And the reason why this works, ladies and gentlemen, if I refer you back to our pyramid, remember in our math pyramid that multiplication, and for that matter division as well, but we haven't done this much with that, but multiplication will distribute over addition and over subtraction. And the reason why that works is because they are within one step of each other on the pyramid. They are closely related enough that they can distribute. Now, we don't call it the distributive property. That's basically, though, what we're looking at today, that exponents and roots actually can also distribute over multiplication and division. So what we see here today, this time I just used an A and a C, whereas on the paper I used AB, but it's the same idea. My root will distribute over the multiplication. So square root of A times square root of C. The same property, the same basic concept works with an exponent instead of a root. So if we have an exponent of a product, that exponent will distribute to each of the things in the product. But a word of caution here, and I want to bring this up. Again, these things work because these operations are within one step of each other on the pyramid. This works because they are one step away from each other on the pyramid. However, if you want to do an exponent down to addition, or you want to do a root and distribute it over addition, these are two steps away. Two steps away. This is not closely related enough. It will not work. So if you try to take your A plus C to the power of B and just distribute that, it is not equal. If you have a radical of A plus C, it will not distribute. So a word of caution there, you cannot do that. So just a quick example here. If I had the square root then of, let's say, 16 plus 9, this would not be equal to the square root of 16 plus the square root of 9. And if we were to simplify these, we could see it. So 16 plus 9 would be 25. Square root of 25 is 5. Over here, square root of 16 is 4. Square root of 9 is 3. And 4 plus 3 is 7. It should be real easy to see there. Those are not equal. So word of caution here. These properties work when the operations involved are one step away from each other. They do not work when the operations are two steps away from each other, like roots and addition. So anyways, back to the lesson though. We're going to focus on this property right here. We are distributing a root over multiplication. And let's consider here the square root of 12. Now 12 right now is not a product, but we could think of 12 as a product. For example, you might think of 12 as being 4 times 3. So if we think of 12 as being 4 times 3, that means that we can split this up into the square root of 4 times the square root of 3. Alternatively, we could also think of 12 as being 1 times 12. In that case, we could split this up into the square root of 1 times the square root of 12. Of course, working through the factors of 12 here. We could also think of 12 as being 2 times 6. And therefore, we could split this up into the square root of 2 times the square root of 6. Now, if I work my way back here, square root of 2 is irrational. So if I leave it like that, that's the exact answer. Square root of 6 is also irrational, so there's really not much I can do with this. If I come back over here, square root of 1 is really 1. So we have 1 square root of 12, and of course 1 times anything is just itself, so really we just discovered that the square root of 12 is equal to the square root of 12, which we already knew. So that's not truly helpful. But if we come back here to this first one, the square root of 4 is 2. Square root of 3 is irrational, so I'm going to leave it alone. So what we discover here is the square root of 12 actually is the same thing as 2 square roots of 3, or double the square root of 3. Ladies and gentlemen, this is simplifying a square root. The reason why this one worked is because we found a perfect square. So remember, perfect squares are going to have a nice square root. That's why they're called a perfect square. They're the square of something. This is a square root other than 1. So 1s aren't really going to simplify these. But we found a perfect square that goes into 12 that will then simplify when we find its root. So to help us moving forward here, we're going to take a look at doing this simplifying by factoring with perfect squares. And I'm going to be honest with you, this actually is my preferred method when I try to simplify a radical. This is typically the method that I use. And so to help us with this, we're going to actually write out some perfect squares. You've got to have these in your mind. So the first perfect square is 1. However, we're not going to reduce with any 1s, so I'm not going to worry about that. And just to be clear here, I keep using the word reduce. So simplifying your square roots, sometimes we also say reduce the radical or reduce the square root. So just understand when I say reduce, I mean simplify as well. So 1 was my first perfect square, but it's not going to be helpful, so I'm going to leave it off the list. So 2 squared is 4, so 4 is the next perfect square. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. And we could keep going, but that's probably going to do us for our list here. So we've got to have these in mind if we're going to factor with perfect squares. So just as we said before, the square root of 12 then simplifies by choosing the square root of 4. 4 is a perfect square that goes into 12. And then times the square root that we need to complete that 12. So 4 times 3 gives me my 12. We simplify the square root of the perfect square. So square root of 4 is 2. And then whatever is irrational, we leave in a radical. And as I said just a moment ago, we would say this as the number out front, so 2, and then we say square roots of, and this is plural because 2 is going to make it plural, so 2 square roots of 3 is how we would say that. 2 square roots of 3. And so my simplified answer is right there. Let's take a look at another example. Square root of 32. So square root of 32, you might recognize again that 4 goes into that. So 4 times what is 32? 4 times 8. So if I simplify now, square root of 4 is 2. So this is 2 square roots of 8. But here's the thing. Just like reducing a fraction, just because you've reduced it once doesn't mean it's completely reduced. The same is true of our radicals, of our square roots. Just because we reduced it once does not mean that it's completely reduced. So is there another perfect square that can go into 8? Well, obviously there is. 4 will go into it again. 4 times 2 is 8 though. So square root of 4 times square root of 2 would give me back my square root of 8. So now I have 2 square roots of 4, square root of 2. Well, simplify this further. There's my 2 out front, times square root of 4 is going to give me another 2, And then this guy is irrational, so just leave him. Finish it off. 2 times 2 is 4. And then there's no way that I can simplify a square root of 2 more, which means that 4 square roots of 2 is my answer. Now, ladies and gentlemen, some of you at this point are going through and thinking, oh, yeah, that's kind of long, but okay, that's just what we got to do. And others of you are probably chomping at the bit saying, but we could have done it faster. We could have done something bigger. And you're right. Just like with fractions, when you reduce a fraction, if you choose a smaller factor to reduce by, you're going to take longer to reduce. If you choose a larger factor to reduce by, you reduce faster. So choosing the biggest perfect square that goes into this will reduce it the fastest. So yes, 4 does go into 32, but 16 does as well. So if instead I make this the square root of 16, and 16 times 2 is 32, then the square root of 16 is 4. My irrational radical stays the same. And look, we have the same answer, but with a whole lot less work. So ladies and gentlemen, I highly, highly recommend that just because you found a perfect square that works, check and see if you can find a bigger perfect square. All right, we're going to do a couple more like this, and then we're going to learn a different method for reducing our radicals or simplifying our square roots. So square root of 18 should be a fairly easy one. I recommend pause the video, see if you can give this a shot yourself. So here I go. Perfect square that goes into 18 is 9, and it's going to be 9 times 2 that will give me back my 18. So square root of 9 reduces down to just being a 3, and then square root of 2 is, well, just stuck as itself. So the square root of 18 is really 3 square roots of 2. And then one more example, we're going to put it right here. Go ahead and give that one a shot. And here I go. Perfect square that goes into 75. Think quarters. 25 goes in. It goes in 3 times. So 25 times 3 would give me back my 75. Well, the square root of 25, of course, is 5. So this is 5 square roots of 3. So the next method that we're going to take a look at for solving these is what we're going to call the prime factorization method. And at this point, I know some of you are wondering, well, which ones do we have to use in our homework? Well, you can use any method you want, unless the directions tell you otherwise. So, again, my favorite is just factoring it. But we'll try this out here. First example we're going to take a look at is the square root of 343. So when it comes to this, I'm going to prime factorize this, so I need to know then, am I going to use a factor tree or division by primes? For this one, I'm going to choose to use division by primes. So remember, we're going to make an upside down division box. And now I'm looking for a prime number that goes into 343. Well, obviously 2 doesn't. You could check 3. 3 doesn't. 5 doesn't. 7. Well, let's try 7. Let's do a little short division to see if it works. So 7 does not go into 3, but 7 does go into 34 4 times. 7 times 4 would be 28, and then 36, or it's going to be 34 minus 28 will give me 6 left over. 7 goes into 63, 9 times evenly. It did work. Okay, now it should be pretty obvious. 49 is not prime, but 7 goes into it as well and goes in 7 times. So actually this is 7 times 7 times 7, or 7 cubed. But I'm not going to write 7 cubed, because what I'm going to do now is I'm actually going to make 2 radicals because I want to split this up. And in the first radical, just like we did above, we're going to put all of our squares. So whatever we can put 2 of together. So I can put two of my 7's together to give us 7 squared here. In the next radical, we're going to put the non-squares, or in other words, everything that's left over. So if I put two of my 7's in this radical, we'll have one more 7 left over there. Now the nice thing about this method here is that the square root will cancel the square. So when the square root cancels the square, I'm going to be left with a 7 that is no longer inside of a square root. But then this guy, well, there's nothing to cancel. There's no square on this 7 to cancel with, so it means he's still stuck inside. So 7 square roots of 7. All right, next example, we're going to take a look at this square root of 112. So to prime factorize this, I'm actually going to use a factor tree, because one of the things that catches my eye about this is I know that 4 goes into 100 because I'm thinking about quarters. I also know that 4 goes into 12. So put it together, 4 must go into the combined amount. Well, 4 goes into 100 25 times. 4 goes into 12 3 times, and if I put that 25 together with that 3, this must be 4 times 28. From here, 4 is going to split up into 2 times 2. Those are prime, so that's done. 28 will split up into, let's make this 4 and 7, because we already know that 4 is 2 times 2, and then 7 is prime. So I'm going to make two radicals again, one for the squares and one for the non-squares, the leftover. Well, here, there's a pair of 2's, so I can put a 2 squared in, but I've got another pair of 2's, so I can put another 2 squared in. So a pair of 2's makes 2 squared, another pair of 2's makes 2 squared, and the only thing left over then is 7. This square root will distribute to both of those and cancel out both of them. So then we'll just have a 2 times 2 without a square root symbol. But the 7 is still stuck behind. Finish it off, 2 times 2 is 4. So 4 square roots of 7. And I'm running a little low on space, so I'm going to go to the back for this next one. If you've got space for another factor tree or division by primes, you can go ahead and stay on the front. But I got to go to the back. So one more prime factorization example, the square root of 600. So 600, I'm definitely going to do a factor tree because to me it's pretty obvious this is 6 and 100. We know that 6 is 2 times 3. We know that 10 is, or excuse me, 100 is 10 times 10. And then both of these are 2 times 5. So now I'm going to make my radicals. Remember, the first radical is going to be all of the pairs. So I can make a pair of 2's right there. So that's 2 squared. I can make a pair of 5's. So that's 5 squared. And then I don't have anything else I can make a pair out of because I got a 2 and I got a 3 left over. So those aren't going to make a square. So it's a 2 and a 3 left over. Well, just as we did before, the square root will distribute and cancel the squares. So this will just be 2 times 5. And then I'm going to go ahead and simplify that. 2 times 3, this is the square root of 6. 2 times 5 is 10, so it is 10 square roots of 6. So, ladies and gentlemen, the reality is when you are free to do this on your homework, when there aren't any instructions given, give me a dashed line there, I highly recommend that you get flexible in your thinking and do a little bit of a hybrid of these two methods, especially if you're feeling a little stumped about something. So as long as the directions don't give you anything you've got to do, consider a hybrid. So if I'm looking at 343 again, And I'm feeling a little stumped about that. So I say, all right, I'm going to start doing division by primes. I'm going to do 7, and we got our 1 in 4 times. We had 6 left over. We got a 9. And I look at this, and I recognize, hang on a second. 49 is a perfect square. At this point, I'd probably just stop and write it out there. Because now we know that the square root of 49 is 7, and this guy is irrational, so he'll just stay the same. So I don't really have to complete my prime factorization. If we find a perfect square, we could just move on. As long as the directions don't say you've got to use prime factorization, you could stop part of the way through. For example, another possibility here, we look at 112 again. So 112, we had that. We figured out it was 4 times 28. Well, then I might think about 28 and think, okay, 28 is 4 times 7. I got 2 4s. I might stop my prime factorization right there and say I've got a 4 squared and a 7 left over. So it's not fully prime factorized, but I found a perfect square. So the square root of 4 squared, the square root will cancel the square, so that's just 4 square roots of 7. Likewise, square root of 600. So this one I know is pretty obvious, but still, just to hammer home the point. If I started prime factorizing this and saw, oh, 100, 100 is a perfect square, again, I would probably stop and just go ahead and write it. Square root of 100 is 10, so it's 10 square roots of 6. So once again, on the homework, feel free to use a hybrid of these two methods. As long as what you do is mathematically sound and you're following the directions and your work is clearly communicating, there is a little bit of flexibility with these problems. If you have any questions, please contact me to make sure that you are using a method that will work. But otherwise, good luck. And that's the end of our lesson.